All right, welcome back again for another episode of Con-E 352. Today we're going to be talking about centrifugal pumps. Now, this is a lecture I would really prefer to do in person. I have this large centrifugal pump sitting at the back of the classroom. Makes a great demonstration subject so that you can actually see the parts and the pieces, and I can describe them to you and describe how the whole process works. Pictures of a centrifugal pump don't do it justice really, but I'm gonna try. All right, we're gonna do our best because you need to learn about pumps and you need to learn about pumping systems. I want to explain the operation of pumps and their purpose because I don't really think your fluids classes gets to the heart of it, especially the important parts about operationally understanding pumps and pumping. So first, this is the picture that I have here and that I have loaded onto Canvas page. This is an in-suction top discharge centrifugal pump. Some important parts about this. Right here, in suction. So there would be a pipe here, right? This would, we connect that to a pipe and it would actually suck water in here into the center of this pump. Then it would go into the impeller. The impeller is the part that you can't see. The blue part here that you can see, right, that is the casing. That's the casing of the pump. All right, it's the part that, think of it as like the outside shell of it, if you will. The part that turns and actually forces water through the system is the impeller, and that's the interior part that you can't see. So the outside here is the casing. Now, this is the mechanical part on the left side. The yellow item there in that picture, that is the coupling. That's actually a guard for the coupling. That is where the mechanical part, the shaft that goes to the impeller, connects to the shaft that goes to the motor. On the far right part of this picture, the back side of this, that's the motor side. So we connect the motor to the impeller, and then that part in the middle, the coupling, connects the two. So that when we turn the motor on, and the motor is going to spin round and round, it's going to spin the mechanical part, the impeller, around, and that is what is actually going to force water through our system. The whole purpose of the pump is to take that electrical input energy and translate that into flow energy. And the more efficient a pump is at taking that electrical input energy and translating it into flow energy, the better the pump is going to perform. Now we're going to take a look at some pump curves and try to learn a little bit about the pump itself. But here, I'm going to blow this up a little bit. Go through this again. Right? This is the suction that goes into the impeller. We'd have a pipe on here. This is the discharge, the top part. We'd also have another pipe there. The impeller spins round and round, and we can't see that. It's inside of this blue casing. And then the motor, it's the electrical part. That's where we take the electrical energy input. We turn it into rotational energy, and then we turn that into flow energy, right? And as a mechanical designer, if you're designing a system, you've got to get all parts and all pieces of that. You've got to select that all properly for it to work right. All right, now let's take a look at some of the other pictures. So this is just a drawing of what I just described, the suction going into the impeller. The center of that impeller is going to be called the impeller eye. The impeller spins round and round and forces the water out the discharge and down the pipe. At the center of this impeller, when it starts spinning round and round, the pressure there at the center drops. That's going to be the lowest pressure. That's how it is able to suck water into it. That pressure drops down. And then at the discharge, that's going to be your maximum pressure. In other words, both the speed of that water, we're forcing that water down the pipe, we're giving it some pressure, and we're also imparting a velocity to it. So it's moving at a high rate of speed when it leaves the discharge. All right, let's take a look at what we call an impeller curve. I have a couple of these loaded on Canvas as well. If you want to stop, and if you don't have these printed out or you want to call them up on your computer, please do so now. I want you to think of this impeller curve as all of the possible combinations of flow in gallons per minute down here at the bottom and pressure. That's what this column here is, and we're going to list that in feet of head. This could also be PSI. It's a simple conversion that we've already looked at. This capacity could be, instead of gallons per minute, it could be liters per second. It could be any volumetric flow rate. And this could be any pressure. But I want you to think of this graph as all of the possible combinations of flow rate and pressure that a certain pump can generate. Now notice, these curves that go this way, these are impeller curves. This is, for a 9-inch impeller, it can develop all of these possible combinations of flow and pressure. Now, if we had the same pump case and we increase that to a 10.5-inch impeller, that's this blue line that goes down there. Those are all the possible combinations of flow and pressure. And if we took it all the way up to an 11-inch impeller, those are all of the possible combinations. And for a given pump casing, right, that's this range, it could have a range of impeller sizes. Like if we go back to this, for a given pump case size, we could put a range of impeller diameters in here. It's not just, you don't just have one casing size and one impeller size. We could get a 9-inch impeller, 9.5, a 10, whatever. We could get a wide range of impeller sizes. So think of this diagram as from 9-inch to 11-inch impeller for this particular pump casing. And notice, it is at 1,750 revolutions per minute. At that combination of impeller, pump case, and motor speed, these are all the possible combinations of flow and pressure that particular pump can generate. Notice on this one, we have selected 8, if you look at the far right side at the top, it has a design capacity of 800 gallons per minute at 7, right here, at 75 feet of head. That is where the pump will be operating. Now, notice, you see these curved lines. Those are lines of pump efficiency. The best efficiency point on this pump would be right here in the middle. So as you're picking pumps, you want to pick them with the best efficiency point possible, but you know, there's going to be certain ranges of acceptable that you can operate a pump at. And then these lines here, I want you to pay careful attention to these lines that start down here and go up here. These are lines of constant power. Now, is your pump going to operate right on one of those lines? Probably not. But those lines represent lines of constant power. In other words, those represent common motor horsepowers that we could actually purchase. We are not going to custom make a motor for your particular pump. You're going to buy a motor, and most likely you're going to buy one, a standard size, kind of off the shelf. And that's what these sizes, this is a 15 horse, this is a 20, this is a 25. Now notice here on this one how close that is to the 20 horsepower line. But the 20 horsepower line never crosses this particular impeller, right? What that means is no matter what combination of flow and pressure we're going to operate at, this pump won't overload this motor. And yes, that is actually possible. You could overload a motor. In other words, here, when you connect a motor to a shaft and you turn it on, motors are relatively simple electrical items. They are designed to operate at one speed. They're governed. That's all they know how to do. They're going to consume electricity until it operates at that speed, right? If it can turn at a rate where it draws more power than the motor is rated for, that is a possibility. Here, I've got another motor pump curve. Let's take a look at this one. I should have both of these pump curves on on Canvas for you to look at. See this one? Let's say that we were to operate this pump was operating at 800 gallons a minute and about 53 feet or so of head at an 11.375 inch impeller. We'd be operating right about this point. Notice we'd be between the 10 horsepower line and the 15 horsepower line. You might say, well, let's put a 15 horsepower motor on because it would work for this particular impeller at this particular duty point. That is correct, it would. However, if something was to happen and that pump started operating at a higher flow rate, then it could potentially move this way on the curve and actually overload, and that's what we would call an overloading pump curve. Well, how could that happen? Let's just give an example. When a mechanical engineer picks a pump, they are usually doing it in the design phase well before the pumping system is actually laid out and well before it's actually put into the building. In other words, from your fluids classes, you know that the total hydraulic resistance to flow, in other words, the pump head, is an unknown. You are calculating it, but that's an estimate, really. It's not a guarantee. Many times, designers are going to overestimate the resistance to flow. So think back to that boiler system and pumps that the flow diagrams that we looked at for the last lecture. And for me, that was just earlier today. But maybe you watched that lecture a few days ago. Well, if that's the case, you might know the gallons per minute that you need to put through a system, but really, you don't know the exact pressure loss until you add up the resistance for every pipe, elbow, and fitting, and twist and turn in the system. During the design phase, you're going to have to make an estimate of what you think that resistance to flow is going to be. Most likely, most engineers, if they're cautious, they are going to overestimate the pressure loss through their system. In other words, if you've got to choose between being high and being low, you say, well, I'm going to overestimate the pressure drop through this pipe so that I know I have enough pump capacity. A reasonable assumption. However, when you do that, your actual operating point will go towards lower head loss and higher gallons per minute. Think of it this way. It's kind of like if you thought you were going to put, let's just say that we had a hose bib, and we weren't sure about the hose size that they were going to connect to that hose bib. Maybe it could be a 1-inch hose, maybe it could be a 2-inch hose, like a fire hose. We say, well, I don't know what it's going to be, so I'm going to estimate a smaller hose with greater pressure loss to make sure that I've got enough pressure there to get water through the system. All right, if that's the case, but you actually put a bigger hose on there, it's going to have less resistance to flow, so you're going to get more flow through that. If we're designing a boiler system, hey, that's not the worst thing that could happen, extra flow rate. However, notice that as we ride the pump curve to the right, we're going to consume more and more and more power, and we could potentially be in a situation that we overload that motor. That motor is going to try to spin at whatever speed it's designed for. This one happens to be 1150 RPM. It's going to spin at whatever speed it's designed for and consume as much power as it needs to do that. If you need a little review on motor theory, talk to Jimmy in electrical class, right? But it's going to spin and draw as much power as it needs. If it goes too far past here, it could easily burn up the motor that is attached to it, and that's what we refer to as smoking the motor. Now, there's something worse that can happen than that, actually, as well. What can also happen is if we really, really overestimate it and we end up going too far down on this curve, what we might run into is a term called, let's see here, net positive suction head required. That is the minimum inlet pressure that we have to have on that impeller to avoid something called cavitation. If we draw down, and this will usually happen when we have higher and higher flow rates, notice the minimum pressure on the impeller as we go further and further to the right at higher and higher gallons per minute, we have a minimum pressure on that inlet. Let's go back to our picture right here, that has to be maintained in order to avoid cavitation. All right, so what is cavitation? I've got a video here that I found. Okay, we'll just take a quick look at this. Cavitation is when bubbles start to form at the low pressure point. The low pressure point on a centrifugal pump is going to be here at the inlet. A bubble will form because that pressure is getting too low. There's the impeller to make water flow through the pump, right? It's going to spin round and round, and you see those impeller vanes here in just a second. As that spins, the impeller vanes push the water out in all directions, and the lowest point of pressure is going to be there in the center, right? It's going to spin, push water out in all directions. Out here at the outlet, that's where pressure and kinetic energy is at its greatest. But at the center, the eye of the impeller, where the water is getting sucked into, that's going to be at the lowest pressure, right? This is a pipe that goes to that in suction. Right there has to have a certain minimum pressure to avoid that term called cavitation. All right, so what does cavitation look like? Right. Oh, and this is also why there's limits to how far out of a tank an impeller can actually suck water into it. There's also a minimum amount of, a pump has to be primed. In other words, there already has to be water in this pipe for it to suck more water out of there. It can't just be sucking air. Now, some pumps are meant to be self-priming, but most centrifugal pumps for HVAC applications are probably not going to be self-priming. So why is cavitation bad? It's only a little air bubble, right? All right.
This material can be damaged.
Well, this will illustrate, right? Think of this as a tiny, tiny microscopic bubble. Maybe a millimeter or two wide, maybe even less. And this gray area represents the impeller of a pump. As the pressure goes from the lowest point at the eye through the impeller and out to the edges of that impeller, at some point, that pressure is going to cause this bubble to increase and then drastically decrease. You'll actually get a little implosion of it and a little microjet of water screaming out from the center of that collapsing bubble. Over time, when this happens often enough, this jet can degrade the impeller material itself, even steel. And we have an example of a normal impeller, one that wasn't subjected to cavitation, right? This one happens to be brand new. And then these gray areas illustrate after a few months of cavitation, 12 months of cavitation, and then a year of cavitation. What you'll see is the metal wearing away at the edges of these surfaces, all right, start to erode the blue finish off of them and actually rip apart the impeller itself. This can happen on any impeller material, whether it be brass or steel, even stainless steel. This will happen. And then over time, as that happens again and again and again, it can erode it. In severe cavitation, you may not have 12 months. On very, very severe cavitation, the pump could actually shake itself apart. On one project I was on, this happened in a 100 horsepower motor, or a pump with a 100 horsepower motor on it, and it had 10-inch supply and return pipes attached to it, and actually sat there and ripped the motor off of the motor mounts. It can be a very dangerous situation if that was to happen. So you just have to make sure that, one, you pick the right pump. Two, you know the appropriate combination of impeller size, impeller diameter, speed, and motor draw. To avoid smoking a motor, make sure that you have not selected a motor size that crosses this impeller curve. That would be called an overloading pump curve. Do not do that. As a cautious engineer, even if I was operating here, if the 15 horsepower motor intersected this 11.375 inch impeller at any point, I would go up to the next larger motor size. You're not going to overload a motor by oversizing it. Yes, it might be a little more expensive. However, you're going to ensure that it never even comes close to operating at its operating duty point. In other words, if a motor is rated for 20 horsepower, why would we want to operate it above 20 horsepower or even right at 20 horsepower? It will last a lot longer if we don't push it close to its rated duty point. All right. Now, I do wish I had my demonstrator, all right? But here, I'm going to try to, let's go back to this other curve. Notice this curve never actually crosses the 20 horsepower point, right? Notice, see where it says BHP and max BHP for impeller. BHP stands for brake horsepower. The actual horsepower that the pump motor is consuming is brake horsepower. Brake horsepower will vary depending on where it's operating at on this curve. If we were operating back here, we'd be operating closer to 15 brake horsepower. Over here, we're operating closer to 20. Notice the maximum brake horsepower for this particular impeller is at 19.82 brake horsepower. Question might be, should we go up to a 25 horsepower motor? In my experience as an engineer, I never like to operate within 10% of the rated nameplate horsepower for a motor. In other words, if I expected to operate here day in and day out, I would have picked the 25 horsepower motor even though its operating point was just slightly less. I don't like being that close to an operating point. Would it work? Yes. Would it lower the life expectancy of this particular motor? Most likely. Is that gold plating it? Or in other words, are you just being overly cautious and causing extra cost to an owner? Perhaps, but in personal opinion, I don't think so. I think this is ensuring that they get a reliable, long-lasting design instead of one that they would have to fix and repair quickly. All right. So, with that in mind, right? With that in mind, some things that you need, some takeaways that you need to get from this. If I give you, like say on an exam someday, if I give you a combination of flow rate and pump head, I would expect you to be able to look at a chart like this and pick which impeller on here that you would have to use. I would also expect you to be able to tell me about what efficiency that it is operating at. In other words, if wherever that point is, right, we could say, all right, I'm operating at 77% efficiency. Maybe I was right here. We could say, all right, we're between 81% efficiency is here, 83 is here. Maybe that's like at 81.5 or something. I want you to be able to look up the efficiency and figure out about where it's at. I would also expect you to be able to give me an approximation of the operating pump power. In other words, if I'm between the 15 horsepower curve and the 20 horsepower curve, I'd expect you, to be able to roughly approximate it. And I would also expect you to be able to pick which motor would be the best choice for operating based on the guidelines that I've given you. All right. So let's pause here for today, and I think the very next week we're going to be getting into fire protection, and also I'm going to be going over, hopefully tomorrow or Friday, maybe this weekend, I'll be making some videos that go over the homework for plumbing. So if you haven't already done that, please give the plumbing homework a try. All right, thank you, and we will catch you next time.